Hello and welcome to ICND2 Lab 6, Understanding EIGRP Metric Calculations. This lab shows how to change some of the settings on interfaces, particularly the bandwidth and delay settings, to influence the route that EIGRP chooses. For those of you following along with the Cisco Press books, note that the material covered in this video is also covered in the ICND2 books, Chapter 10. This lab has three main objectives. First, this lab helps you understand which interface's bandwidth and delay settings impacts EIGRP's metric calculation for a particular route. Then you'll learn how to explain how EIGRP uses the slowest or constraining bandwidth as well as the cumulative interface delay to calculate its metric. Then you'll have a good idea of how to predict the impact of both the bandwidth and delay settings on an interface and how changing those settings might impact EIGRP's choice for the best route. This video uses two main scenario steps to demonstrate how EIGRP works with metrics. In the first step, you'll analyze the differences between the EIGRP metrics for two possible routes to reach a particular single subnet. In the second part, you'll predict the change in the EIGRP metric calculated by a particular router based on the changes to that interface's bandwidth setting. To start scenario step 1, let's take a look at the topology and IP addresses used for this particular video. For those of you that have already watched ICND2 Lab 5, it's the same topology, IP addresses, and masks that were used in that video. For instance, here we have three routers and a triangle of serial links, each with a fast Ethernet interface. The IP addresses are shown there, and just because EIGRP does support VLSM, different masks are used throughout the network. We've got this 255.255.255.252 mask used on the serial links, and each of the three LAN subnets uses a different mask. /25 on the top LAN, /26 on the bottom left LAN off router 2, and then a /27 mask off of router 3. Also, for reference, the screen now shows the subnet numbers of the 6 subnets used in this topology. For the rest of the lab, it may be handy to have either your soft copy or hard copy booklet that comes with this video product, just so you don't have to keep doing the subnetting math in your head. Now that we have that background information out of the way, let's move on to some of the specifics about how EIGRP calculates its metric. First of all, the interface bandwidth is one of two inputs into the EIGRP metric calculation, at least by default. The interface bandwidth setting is a software setting. In other words, it's configured with an interface subcommand, specifically the bandwidth command. Now this command is just a software setting. It does not impact the actual physical rate at which bits are sent out the interface. For example, in this network, the link between R1 and R2 is actually clocked at 64 kilobits per second. However, as you see here, we're going to default the bandwidth setting to the default serial bandwidth setting of 1544 on both ends of that link. Now the 1544 means 1544 kilobits per second, which of course is 1.544 megabits per second, which is T1 speed. So in this particular lab, we'll default the serial links to use bandwidth of 1544, and the fast Ethernet interfaces will also default their bandwidth to 100,000. Now again, to make the point, that's 100,000 kilobits per second because that's the unit used on the bandwidth command. But 100,000 kilobits is equal to 100 megabits, which is appropriate for a fast Ethernet interface. Next, let's consider the fact that EIGRP's metric calculation uses the slowest or constraining bandwidth, not the overall bandwidth. For example, in this video lab, we're going to focus on the route from router R1 to the lower left-hand LAN subnet. So in this case, there are two routes. There's the route that goes left, directly from R1 to R2, then the route that goes a long way around, that goes from R1 to R3, and then over to R2. However, EIGRP only considers the slowest bandwidth amongst all the links in a particular route. In particular, it considers the slowest bandwidth on the outgoing interfaces in each route. For example, here now the video removes the unnecessary bandwidth from consideration, so it just lists the bandwidth command settings for all the outgoing interfaces in these two competing routes. Well, as you can see here, the slowest bandwidth in each case is 1544. So, from EIGRP's perspective, both routes are equal, at least in regards to bandwidth. EIGRP uses both interface bandwidth and interface delay as part of its calculation of the metric. Now the delay, instead of being the slowest or constraining delay, is the cumulative delay, and it's the cumulative delay for all outgoing interfaces in a route. So if you take a look at the figure here, we overlaid the delay settings on each of the outgoing interfaces on the two competing routes. Now it turns out these are the default delay settings on these interfaces. So if you take a look at the R1 to R2 route, we see that the cumulative delay will be 2010. If you then look at the other route, see the cumulative delay is 2000 plus 2000 plus another 10, or 4010. So as it turns out, even without knowing the details of the EIGRP metric calculation, we can predict that R1 will pick the left-hand path over to the subnet on the bottom left because the bandwidth ties between the two competing routes, but there's a smaller cumulative delay over the route to the left. Now, I can't imagine the specifics of the metric calculation are going to matter for the CCNA exam. However, it's a good place to show you the formula. So here we have the generic formula in its default state. In other words, EIGRP by default only considers bandwidth and delay, and here's what the formula reduces to. So for the best route in this case, the route from R1 to the subnet on the left that goes directly to R2, let's plug in the slowest bandwidth and cumulative delay. As you see here, we move 1544 up for the slowest bandwidth, and 2010 for the cumulative delay. Now you can do the math yourself. I'll show you the steps broken down a little bit here just for reference. There's the math inside the parentheses. There's the multiplication by 256. Then add them together, you get 2,172,416. The number itself is not all that interesting, but we'll see that in several of the show commands coming up next. So now let's transition over to the command line interface for this particular network. We'll spend our time in router R1 because it's the route on router R1 to that bottom left-hand subnet that we care about most for this example. So if we do a show IP route command here on router R1, let's go find that subnet. Here it is. It's 172.22.12.192 with a /20 fixed prefix length. Now note, inside the brackets we've got a couple of numbers. The 90 is the administrative distance for EIGRP, the default administrative distance. The second number is the metric. As you see there, it's 2,172,416. This value indeed matches the number that we calculated just a few moments ago here in this video. A few other details that are interesting. Notice the via field points to 172.22.112.102, which if you look at your IP address reference, you'll notice that that's R2's serial IP address. Also as a reminder, it lists serial 010, that's R1's interface serial 010, as the outgoing interface. Once again, a confirmation that this route is the route directly from R1 to R2. Next, let's take a look at the interface bandwidth and delay settings on R1's serial 010 interface. So if we do the show interfaces S0/1/0 command, and you looked up toward about the third or fourth line in the output, you see both settings. Now the bandwidth is relatively obvious. It's preceded by the letters BW, and it says 1544 kbit, reminding us the unit is kilobits per second, and there's our 1544 value, which is the default on serial interfaces on Cisco routers. Now the delay setting's rather odd. Instead of saying delay, it says DLY for short, and notice here it says 20,000 USEC or microseconds. When you do this show command, it lists the delay setting and the number of microseconds, in this case 20,000 microseconds. Oddly enough, the configuration command that configures the delay command, as well as the EIGRP metric calculation, uses a different unit. Instead of using microseconds, it uses tens of microseconds. So that 20,000 microseconds is the same as 2,000 tens of microseconds, which is why we fed in 2,000 for the interface delay when we showed how to calculate the metric. If you go over and look at the settings on the Fast Ethernet interface, we see some similar ideas there. We have BW for bandwidth, and it says 100,000 kilobits, and the delay setting of 100 microseconds, which is the same as 10 tens of microseconds. Next, let's move on to scenario step 2 for this video lab. This step is relatively short, and in this step we'll change from using the default bandwidth settings to using more accurate settings. Two of the serial links are actually T1s, but the link between R1 and R2 actually uses a 64 kilobit per second link. So there on R1 we're going to change the bandwidth setting using the bandwidth command to bandwidth 64. That means the route from R1 directly through R2 will now have a new constraining or slowest bandwidth of 64K. Now if you compare the two alternate routes and ignore the EIGRP formula, it's hard to tell who's going to win. The left-hand, more direct path has a much slower bandwidth but a much better delay, whereas the long path has a better bandwidth setting but a longer delay. Well, it turns out in this case, the longer path, the path from R1 through R3 over to R2, will end up having a better metric. So let's turn our attention to router R1 again and confirm first with the show interfaces command that interface serial 010 indeed still has a bandwidth setting of 1544, which it does, as you see here. That's the default setting. So if we then go into configuration mode, get into interface serial 010 configuration mode, as you see here, and then type the bandwidth command with a setting of 64, meaning 64 kilobits per second. Now if we exit configuration mode and repeat the show interfaces command for serial 010 and look for the bandwidth setting, notice it simply says bandwidth 64 kbit, which is exactly what you'd expect at this point. Next, to confirm that this did indeed impact R1's choice of best route, let's repeat the show IP route command. So if we look down and we find the route to the lower left-hand subnet, as you see highlighted here, subnet 172.22.12.192, notice the second number in bracket, the metric, is indeed larger at this point. Notice it's 2,600,000 and change, whereas earlier the metric was 2,100,000 and change. Also note that the via field points to an address that ends in 113.210, which if you look at your IP address reference, you'll notice that's R3's serial IP address. Finally, R1's outgoing interface listed at the end of the route, serial 011 now, that's the serial link that, according to our topology diagram, connects R1 to router R3. This concludes ICND2 Lab 6. In this lab, you've understood which interfaces, bandwidth, and delay settings impact EIGRP's metric calculation. You've learned how to explain how EIGRP uses the constraining or slowest bandwidth and the cumulative interface delay when calculating its metric. Finally, you've seen how to predict, to some extent, the impact of changing an interface's bandwidth setting on the metric that's calculated by EIGRP.